Hello everybody, my name is Arseni Girgis, a fourth year PhD student at EPFL in Switzerland, and in this talk I'm going to present our paper, GARFIELD, System Support for Byzantine Machine Learning. This is a joint work with my colleagues Jeremy Plasman, Anton Rago, and Sebastian Rouault, and my advisor Rashid Garawi. Let's start with the basics. This work focuses on the training phase of machine learning, in which you have some dataset and some model, and you'd like to use this dataset to train that model to do some task. For example, let's say you have few images for cats and dogs, and you'd like to train that model to tell whether this image is for a cat or a dog. It's kind of given now that for scalability, machine learning algorithms should go distributed. And by scalability I mean two things. First, the sizes of the state-of-the-art models are getting bigger and bigger every day. Take, for example, the huge sizes of today's state-of-the-art language models. Such models, obviously, cannot be trained on a single machine. Second, the huge datasets that can be leveraged for better ML models. Taking into account that this dataset is naturally distributed in multiple machines across the world. Think of the amount of data generated from your phone by taking pictures with your camera, recording audio, or typing on your own mobile keyboard. Yet the moment you distribute learning on multiple machines, the moment you increase the probability of failures on one of these machines. The most general way to model failures in the distributed computing world is to assume arbitrary failures, which are also called Byzantine failures. Byzantine failures abstract machine crashes, network commissions, software bugs, hardware defects, and worst of all, malicious attackers. Not to mention that ML is nowadays used in mission-critical applications like content moderation and self-driving cars. Taking care of such attacks is necessary. Here is an example on what can go wrong with distributed ML deployment with even one Byzantine machine. This distributed architecture shown here in the slide is called the parameter server architecture. This one is widely used and accepted by the ML and systems communities. In this architecture, you have one central server, which is also called the parameter server, which holds a model that you'd like to train, and bunch of machines, which are also called workers, which hold collectively the training data. A training iteration starts with the server sending the model to the workers, which compute updates based on their own local datasets. After doing that, workers send the updates back to the server, which aggregates these updates typically by averaging, and updates the global model. It has been shown before that even if one of these machines is Byzantine, the whole model fails to learn correctly. Note that these workers are not replicated, which means that the data they own are different from each other. So the updates they make are not identical, and that's why vanilla consensus algorithms would not work in this case. This problem has been extensively studied in the past few years in top theory and ML conferences like NeurIPS, ICML, ICLR, POTSI, and more. Yet a very little attention has been given to apply these theoretical solutions in practice. Also, it's not straightforward to build such Byzantine solutions on top of popular ML frameworks like TensorFlow and PyTorch. The reason for that is basically that these frameworks are designed in a way to give high performance with respect to throughput without giving so much attention to Byzantine fault tolerance. One example would be the shared graph design, which is followed by TensorFlow. In particular, all machines in a distributed deployment in TensorFlow have access to a shared memory abstraction, which stores the learning state. A malicious user can change the state to whatever it wants, affecting the whole learning procedure without anybody in the network knowing what the problem is. Another example would be the high-level communication abstractions that are typically given by these frameworks. In a robust ML deployment, a more fine-grained abstractions are required, which are not offered now by the popular ML frameworks. To mitigate these problems, we propose GARFIELD, a library to build Byzantine ML applications on top of popular ML frameworks like TensorFlow or PyTorch with minimal engineering overhead. The key is to think of the distributed ML deployment from objects perspective rather than from algorithmic perspective. In particular, GARFIELD provides abstractions for two main objects to handle the training: servers and workers. The server is the one that orchestrates the training procedure. It stores the model state and it asks the workers to compute some updates from time to time. The second key component in our library is the robust aggregation box, which implements a state-of-the-art robust aggregation rules which can be used to mitigate Byzantine updates either from workers or from servers. We used GARFIELD to implement 3 Byzantine ML algorithms which correspond to 3 distributed architectures. The first one on the top left of the slide shows the typical parameter server architecture with one server and multiple workers. The one next to it allows for multiple server replicas, basically to tolerate Byzantine servers in addition to tolerating Byzantine workers. The third one at the bottom shows a fully decentralized peer-to-peer setup with no distinction between servers and workers. In this setup, basically, each machine works both as a server and as a worker. Here is an example on how you could write a distributed ML algorithm using GARFIELD. This shows the pseudocode for the multiple servers and multiple workers setup. Such a deployment tolerates both Byzantine servers and Byzantine workers. This is the code for the server side. Lines 1 to 3 show the initialization part, including initializing the training objects and the robust aggregation rules. The rest is the training part. In each iteration, each server asks all the workers first to compute the gradients given the current model state. After collecting the gradients, the server applies some robust aggregation rule and then updates the model using the aggregated gradient. In order to tolerate Byzantine servers, all servers communicate the updated models and aggregate them using some robust aggregation rule, and store the new aggregated model as the current model state. From time to time, servers can compute the accuracy of their model states, and this can be used by the users as a sanity check that everything is progressing as expected. Now let's move to our results. The first aspect we looked at is the convergence of learning in the Byzantine environment. We compared the 3 architectures we built with GARFIELD to a vanilla PyTorch setup and a crash-tolerant setup. We found that although in general convergence can be achieved even in the presence of Byzantine machines, there is a convergence penalty that arises due to the usage of Byzantine resilient aggregation rules. In addition, we can see that the penalty depends on the deployed architecture. For instance, the decentralized architecture suffers from the biggest convergence penalty, basically due to using the robust aggregation rules multiple times in each iteration. Another thing we looked at is the performance overhead of the Byzantine algorithms. We found that the main driver of the overhead is the extra communication required by the Byzantine deployments. In general, communication accounts for more than 80% of the overhead, where robust aggregation accounts for only 11%. We invite you to look at the paper for more results and more details for our systems implementation. This brings me to the conclusion of this presentation, which presented to you our new library, GARFIELD. GARFIELD enables building Byzantine ML applications on top of popular frameworks like TensorFlow and PyTorch while achieving transparency, which means applications developed with either framework do not need to change their interfaces to be made Byzantine resilient. GARFIELD mainly relies on robust aggregation rules to achieve resilience to both workers and servers. We hope that GARFIELD would be used and extended by the ML and systems communities to test the practicality of the new solutions to the current hot research topics, including adding privacy guarantees to Byzantine protocols and improving the communication overhead of such protocols. We have open sourced GARFIELD. You can check it out on this link. With this, I'd like to conclude the presentation. Thank you for listening.